All right. Hello, everyone, and welcome to another ACE talk. We're very happy to have you here, and no matter where in the world you are watching this from, hope you're having a great day. So just before the talk begins, I just want to have a quick reminder that we have a online GAN workshop coming up where we will go through how to design and train a GAN model, deploy the model in a cloud agnostic way, and also build an application. So there is going to be a capstone competition for this, and the winning team will get a full refund of what they paid. So I'm not going to spend too much time on the details here, but Amir will be posting links for more information as well as a discount code to this, if that sounds interesting to you. So today, I'm very excited to have our stream advisor, Matthew Taylor, join us. Matt is an associate professor at the University of Alberta and previously the principal researcher at Borealis Edmonton. And he holds a PhD of computer science from the University of Texas at Austin. Pleased to have you here, Matt. We also have Awesome. We also have co-presenter today here, Sriram. Sriram, Matt, and their team at Borealis AI worked on the research in multi-type mean field reinforcement learning that they will present today. Sriram is a PhD student and researcher at the University of Waterloo, focusing on reinforcement learning. He was previously a researcher at Borealis AI. Thank you for being here today, Sriram. So thank you. Without further ado, I'll pass it on to Matt and Sriram.
Great, thanks, Susan. So Sriram did basically all of the work for this paper, but I'm going to start the presentation with some background and then hand it off to him. Pascal was at Borealis and is now resumed full-time as a professor at University of Waterloo. Nidhi was at Borealis and has now become a professor at University of Alberta. So mean field, multi-type mean field reinforcement learning. There's a bunch of terms here, so we're going to start by breaking these down. Next slide, please. If you're on this stream, you probably already know that reinforcement learning is awesome. One of the places that's been super successful recently is in video games. So things like Go, Dota, StarCraft, things like that. So it's really exciting to see these huge improvements in reinforcement learning. But there's lots of criticism because we're focusing on video games, right? There are so many good successes for supervised reinforcement learning in real world settings that people in companies really care about. Why is RL so focused on video games? Next slide. So one of the reasons is video games are very easy to get results in and they're flashy. But RL is starting to have a number of deployed successful applications. I'm personally most familiar with finance, so thinking about stock trading, portfolio optimization, options pricing, that kind of thing. But reinforcement learning is being used across computer science and in other things like business, energy, and education. So it's important to note that reinforcement learning has been getting a lot of press for video games, but a lot of us are trying to push it beyond that. And that's going to be one of the motivations of this paper. How do we scale reinforcement learning to problems that are important and that we care about? Next slide. Just as a quick backgrounder, in reinforcement learning, you have an agent that's interacting with an environment. The agent's in a state, it takes an action and gets a reward. Unlike supervised learning, this agent is never told whether it's right or wrong. The agent is never said, yes, that was correct, or no, that was wrong, it should have been a 5. Instead, the agent needs to interact with the environment over time. And this environment could be a simulator or it could be the real world. When you are interacting with a simulator, maybe you don't care so much about that cost because it's just compute. But if you're interacting with a real world, if it's a robot, there's real wear and tear on the system. If you're making trades in the stock market, you're actively losing money. Well, or possibly getting it if you're lucky initially. So you need to think about how do we learn quickly? And a constant worry is how do we explore versus exploit? We want to leverage our existing knowledge to continue to accrue reward. We also need to think about trying new things to see if I can do something better. Next slide. So like I said, we want to maximize this real value reward. We often think about maximizing the final performance, So can I beat a world-class Go player or not? And if that's your goal, maybe it doesn't matter whether it took you weeks or years to train. But if you want to deploy an application in the real world quickly, you do need to worry about that learning speed. So that's something that practitioners are constantly thinking about, the difference between asymptotic performance and online performance. So I've mostly been talking about the single agent case so far, but now let me switch to the multi-agent case. Next slide. So when I say multi-agent RL, now I'm saying there are multiple actors in the world. So think about playing soccer. My team scores a goal. How do I figure out that good thing we accomplish should get partitioned to the different 11 players on my team? It probably wasn't just the last person who touched the ball who deserves credit for that goal. You can also think about non-stationarity. People on my team might be starting to play differently. People on the opposing team are very likely to start playing differently if they're not doing well. And these kinds of questions make us think that you need to explicitly reason about others in the environment. So a simple approach is to say, I've got all of these other actors, I'm just going to ignore them. I'm just going to think of them as noise in the environment. And in some cases that works. But in a lot of cases, explicitly reasoning about or modeling these other agents is really necessary to get good performance. So if I think about controlling my team, my team of 11 agents on the soccer field, I could think of a centralized approach where I assign each of the 11 players an action on every time step. And that's a huge cross product of actions. And then thinking about the state of all of these agents, now the state or setting that I need to consider is just exploded. One of the ways you can combat this is to take a distributed approach. So each agent thinks individually about how to act on their own, but they still need to think about where their teammates are, what their teammates are doing, and what the opponents are doing. So you get these really interesting and potentially complex behaviors that you don't necessarily even anticipate as a developer. So in a game of soccer, we can think of it as a cooperative game because among my team, I'm competing against the other team. But you could also have cases where it's something in between. So if you're driving in traffic, you don't necessarily care how fast somebody else gets to work. But if you're trying to minimize your time to work and you start driving like a jerk, other people may react to that. So being able to explicitly reason about that is important. And throughout all of this, you often need to consider communication. How are these agents going to talk? So if you find this interesting, I've got a couple of pointers for you. The first is we recently wrote a pretty comprehensive survey on deep multi-agent reinforcement learning, which gives you a sense of what's been going on over the past 20 years, but also provides a quick start on these are the most important techniques right now. So if you're new to multi-agent RL, you might find that interesting. Also, the AMOS conference, the Autonomous Agents and Multi-Agent Systems conference, is, in my opinion, the best conference on multi-agent systems. And that's starting next week on Monday. And for the first time ever, since it's a virtual conference, all the material is going to be free online. So there is going to be a ton of video and other materials that if you are interested, you should check it out for free. Next slide, please. So we can think of Go and chess as being multi-agent because it's two-player, but we can think a lot of other examples are much more than two-player. So we've been talking about soccer. There's the game of Bomberman, which is the partially observable version of the classic video game Bomberman. There's multi-agent Minecraft. And there are other popular benchmarks or platforms where you can investigate reinforcement learning, multi-agent reinforcement learning. But the problem is things are still really hard. So if we want to think about the stock market, where you have many agents or actors, or think about the energy grid, I can have multiple producers of energy and multiple consumers of energy. And I could think about this per transformer, or I could think about this per household, or I could think about it in terms of individual smart applications or individual car chargers. So in order to scale up, we need improvements to our core fundamental reinforcement learning algorithms. One of the recent breakthroughs is thinking about how mean field theory can help multi-agent RL. So at this point, I'm going to hand it off to Sriram, who can talk about mean field theory and then get into the work that he actually did for our paper.
Thanks a lot, Matt. So just to make the setting very clear, we have many agents in our environment, and the current multi-agent reinforcement learning algorithms, that is from literature, are not tractable in this setting. So the primary reason why these algorithms are not tractable is because these algorithms are exponential in the number of agents. So now that we have many agents in the environment, all these moral algorithms, multi-agent reinforcement learning for short, will not be tractable for this setting. So mean field theory is a cool technique that helps us to make moral algorithms tractable. So the mean field theory approximates the net effect of all the agents in the environment into an average agent, which can retain the essential aspects of the system. So intuitively, this technique works because each agent's individual effect can be potentially canceled by other agents doing opposite things in a large environment, and therefore the essentials of the system are still captured. The mean field game, which has been introduced by Lastry and Lyons in their seminal paper in 2007, extends this mean field theory to the to the field of game theory. So all the techniques and principles of game theory applies to the mean field game. So in mean field game, the assumption is that we have large number of rational players who have global information available to them. The meaning of the word rational here means that each agent tries to maximize its own utility. The assumption in the mean field setting is that all the agents are independent and identical. The other way of saying it is the agents are independent and indistinguishable. So this is an important assumption that we are going to keep coming back to. So please remember that. Just moving on. The mean field theory, to very quickly recap, the mean field theory approximates the many agent problem into a two agent problem, where the second agent is an aggregate of all other agents in the environment. So this approximation makes multi-agent RL algorithms tractable because now the problem is just a two agent problem and it's not a many agent problem. The approximation holds only if the agents have similar objectives and abilities. This assumption comes from the mean field assumption of independent and indistinguishable. A very good example where the mean field theory works well is the icing model shown in the first figure here. The icing model is a simple environment where different agents are a magnetic dipole, and they can spin in a particular way to lower the overall energy of the system. In contrast, we can intuitively see that real-world applications are far more diverse with a very diverse set of agents. A good example of a real-world environment is a lecture hall where the professor has to deal with a large number of students with diverse interests, abilities, and knowledge of the prerequisites. Another example is a demand and supply logistics problem. Here, the supplier has to cater to different degrees of demand and supply at different neighborhoods for different people. The mean field assumption would not be valid in such a diverse assumption and at such a diverse environment because the agents cannot be said to be independent and indistinguishable anymore. So to cater to these kinds of environments with very different sets of agents, we introduce the phenomenon of types to the mean field setting. So the types are groupings to other agents in the environment such that members of a particular type are similar in objectives and interest. So from this large environment with many agents, we identify agents which can be considered similar in objectives and interests, and we group them together into a single type. Similarly, we have many different types in this entire environment. The rationale here is that the mean field assumption of independent and indistinguishability is still valid within a type, but it is very hard to justify across types. So just a quick note, as I am presenting the slides, if there are questions, I encourage all of you to ask them in the chat, and I will be taking them up through the presentation. So in this work, we will be analyzing two independent categories of types. The first category we call as predefined known types. Here we have environments in which different types are already known upfront. So good examples where we have a known type environment is multi-party elections with coalitions, because people know upfront like which are the parties that are contesting the election, and people know upfront the coalitions that these parties have entered into. Another example could be different types of sports where you have different players in different teams, and each player has a specific skill set, and they are grouped in based on their skills. The second category that we are going to investigate in our work today is called as the unknown types or no types, where we analyze scenarios in which there are either no teams involved in the competition or the teams are unknown at the start. A good example is stock trading, where there are large number of agents, millions of agents, trading stocks in the stock market, and people have very limited information about what strategies these other agents trading stocks have. Also, a good example is the logistics problem that I briefly mentioned before, or with demand and supply. Here we have huge number of players in the competition, and people don't always disclose business alliances.
A quick question from that slide previously.
Sure.
For the baseball example, so let's say the types, is the types just the class of what team they are on, or is it something about their skill sets as well? Because you mentioned like they have different skills. Their role on the team.
So here we can the types can is a very loose definition, and it can correspond to different things in different environments. So it depends on how a person is modeling the baseball game. So for the baseball game, someone could model different teams to be different types. So then you have two types where the types are two opposing teams. But then you can also model the pitcher and the person who's hitting the ball as different types, if you want to be more explicit about it. So in this slide, we are just saying that types are a very general term. As much information as possible can be modeled at the start of the game, as much as you know.
Gotcha. Thank you.
Is that good? Thank you.
Yep.
So let's move on. So our work builds on the mean field reinforcement learning paper that was released by Yang and others, published at ICMO in 2018. So I will briefly summarize this paper in this slide as it's very related to our work. This paper extended the popular Q-learning reinforcement learning algorithm to the mean field scenario. This paper explicitly assumed that all environments can be represented using a single type. Using the examples we indicated before, this assumption holds for simple environments like the icing model, but it's not very relevant for many other environments. So we will relax this assumption in our work. The mean field Q update that these authors introduced has been proven to converge to the Nash Q equilibrium under certain assumptions. One important assumption that these authors considered was that the Q function is additively decomposable. So just to mention, the Nash equilibrium is a solution concept in game theory where all agents are playing a strategy in which, given the strategy of other agents, no agent will have any incentive to deviate. So now we have given a very good background for our field and for the particular work that we're doing. Now we are going to get into the essential aspects of our work. We will go through this in the order of theoretical guarantees, and then a practical implementation, and then we look at experiments in which the practical implementation performance are studied. So our work on multi-type reinforcement learning assumes that the Q function is additively decomposable using types. So the additive decomposition here is a generalization of the pairwise decomposition to multiple types, where each term depends on a representative agent from each type. So let's consider an environment where there are capital M types of agents. Here, so when I say types, there are these correspond to groups. So let's assume that we have M different groups of agents. We make a mild assumption that we can partition all the agents in the environment artificially into capital X subsets, where each subset has exactly one agent of each type. So to make this very clear, types are different from subsets. Types are groups inherent in the environment, and subsets are artificial assignments made to effectively decompose the Q function. In this equation that I'm presenting the slide, the Q function of a single agent J involves interactions with agents of all types in the environment. Here, the variable S denotes the state. Bold A captures the interaction of the central agent with each one of the subsets using the additive decomposition. So now one question would be how to form these subsets. So let's assume that we have a scheme that assigns each agent of each type to one of the subsets. Note that we do not need each type to contain an equal number of agents in the environment, as we can always make a new subset that contains one agent of a type and other agents to be placeholder agents or dead agents of other types. So we will actually relax this requirement of decomposition shortly, and we do not need to make any subsets in practice at all. So I will just make a quick pause here for questions.
Right.
Are there any other questions, Susie?
Yep. There is a kind of a question that, so they were saying that from their understanding, mean field is when you simplify a harder problem by averaging over some dimensions. Is that what is happening here? How to connect? Is their assumption correct? And how to connect what this is saying to what they're understanding?
Sure. So we made a clear distinction between two different concepts in a slide before. So there is something called mean field theory, and there is something else called a mean field game. So a mean field theory is exactly what the question corresponds to. A mean field theory is trying to take an average over different dimensions to simplify the problem. But when mean field theory gets extended to mean field games, within the game, the average is between the performances or the actions or the effect of different individual agents in the environment. I hope that was clear.
Okay, I think that's right. Thanks. Awesome.
Thank you. Okay, so let's move on. So here I explicitly talk about the mean field approximation that we make in the paper. We use the Taylor's expansion to approximate the true Q function, which is shown on the left-hand side of the first equation here with the state S and the bold A, to the multi-type mean field Q function, which is on the right-hand side. Right, the multi-type mean field Q function involves average actions of all the M types. So here we have one theorem, the first theorem here, which shows that when we additively decompose the Q function, and if the Q function with this wild assumption that the Q function is L smooth, then this approximation gives a good error bound that is bounded by the term 1/2 L epsilon, where L is the Lifshitz constant and epsilon is the average deviation of all agents' action from the mean field of its type. So let's move on. So let's consider a case in which we have an environment with two types and we only model a single mean field. So delta over here in the first equation corresponds to the deviation between an action of an agent and its mean field approximation. So we can then prove that the average delta of all agents can be bounded by this term involving a function of epsilons and alphas. Epsilon 1 here is the average deviation of every agent action of type 1 from the mean field of type 1. Alpha 1 is the difference of the mean action of type 1 from the overall mean field. Similarly, epsilon 2 here is the average deviation of every agent action of type 2 from the mean field of type 2. And alpha 2 is the difference of the mean action of type 2 from the overall mean field. K1 here is the total number of agents of type 1. K2 is the total number of agents of type 2. And capital N is the total number of agents in the environment. On the other hand, theorem 3, the next theorem, shows that if we have two types in the environment and they have been modeled to be different types, we can prove that this bound is given by a function of epsilons only, where all the variables have the same meaning as in theorem 2. So this can be extended to a general M-type scenario as well. We just made a quick example with two types. So we can see that the error bound is lower for explicit type modeling. This result helps motivate our approach by showing that accounting for multiple types can potentially improve performance. So let me make a quick pause here for any questions.
Right. We do have a question. If you could quickly reiterate what the difference between the epsilons and the alphas in the theorem 2 are.
Yes. So epsilon1 is the average deviation of every agent action of type 1 from the mean field of type 1. So epsilon1 is a per agent characterization. So it is an action of each agent and the mean field of its own agent. So it's the difference between action of each agent and mean field of its own type. Alpha 1 is the difference of the mean action of type 1 from the overall mean field. So just to make this explicit, so in theorem 2, we consider a case in which we have two types in the environment, but we are only modeling a single mean field. So therefore, we introduce a variable called alpha 1, which captures this difference between the mean field of type 1 and this overall mean field, which is the only thing that we are modeling. But in theorem 2, we don't have alpha 1 because we explicitly model each type separately.
I see.
Hope that was clear. Yeah. If there are further questions on that, I will take it up in the end.
Okay, there was one quick other question for that slide at the bottom. So explicit type modeling, what does that, could you quickly reiterate what that refers to again?
Yeah, so that's just the difference between theorem 2 and theorem 3. So in theorem 2, I said that we have two types and they have been modeled as a single type. So this is consistent with the assumption of the Yang et al. Paper that I was mentioning, where they assume that all the environments can be modeled using just a single mean field. So in our paper, we do something called explicit type modeling, and we show in theorem 3 that our approach, where we do explicit type modeling, and we will get a lower error bound, as against an approach that was done by Yang, which was presented in theorem 2. So their error bound would be much greater than us.
I see. Thank you.
Thank you. So let's move on. So here we provide the update equations that we use to practically implement this setting. And so the update equations in our work is canonical to the work by Yang. Yang and others released in 2018, the paper released in 2018. So we can see the differences between the equations in the second table, in the second column and the third column, is that we explicitly model types. So we have this characterization of mean actions to M types, whereas in the second column, all the equations from Yang have only a single mean field. So in this slide, I'm going to be dealing with equations in the third column because those are the ones that we introduced. In the first equation, and we have the Q function update that depends on the value function of each state. Then the value function in the second equation and is updated using the product of the probability of choosing an action and the Q estimate under an expectation. So we sum this product over all possible actions. Then the average action is taken using a simple average of all the actions where the action is obtained from the respective policies. And then in the last equation, the policy is updated using the Boltzmann policy, a equation which is done as done in normal practice. So as can be seen, all these algorithms are recursive in nature and all the updates are done recursively until convergence, which is traditionally done, which is the traditional way in reinforcement learning. So to prove the solution concept that we have is rational and that it converges to an equilibrium, we also take three common assumptions as done conventionally in literature. So these assumptions were introduced by a seminal paper, Hu and Bellman, Nash Q Learning in 2003. So the first assumption states that each action value pair is visited infinitely often. That means that you guarantee that every state in the environment will be visited. The second assumption states that the agent policies are greedy in the limit with infinite exploration. The third assumption states that for each stage game, the Nash equilibrium can be considered to be a global optimum or a saddle point.
Oh, we did have a quick question. Sorry to interrupt there.
Yeah, I can take that. I was just going to take questions after the next slide, but I can take a few now.
Okay, thank you. So one question we had about the, I guess, action or action value pairs, do all agents share the same set of actions in, I guess, the research you were talking about? Are the types differentiated based on their reward functions in this case?
Okay, so the mean field assumption is that every agent is independent and indistinguishable. So just to restate that, every agent in this environment is independent, which means that all agents have their own Q functions and they have their own policies. So nothing is shared between anybody. So types are only determined based on the common interests and abilities. So this relation with reward function is actually it's a good point that is being made. We are going to make this explicit in the experiment section. So all the agents are having their own policy and their own queue function, which they update independently, but they could potentially have different reward functions across types.
Gotcha. Thank you.
Thank you. So now we state the mean convergence result of our paper. So in the first equation here, on the left-hand side, we have the variable Q star, which is the Q value of the state in action under the Nash equilibrium. The other Q function is our true Q function, which we introduced before. We can prove that our Q function our Q function will converge to a bounded distance of the Nash equilibrium, and the bound is given by this term 1/2 L epsilon minus S. So the first term over here, 1/2 L epsilon, was already comes from theorem 1. We already introduced that in theorem 1, and capital S, which is a constant, is obtained by this equation given here, or psi C1 plus alpha gamma D by alpha B naught, where here we can fix a arbitrary constant C1 and scale the stochastic process to be below C1 using the scale factor beta naught. The alpha here is the learning rate, and gamma is the discount factor, all of which are fractions by definition, and psi is another arbitrary fraction. So this theorem is an application of a modified theorem by Jekola and others, which has been released in 1994. So should I pause here for a question? Okay, or shall I move on?
I think we're good here. Thank you for asking.
Okay. Thank you. So now with that, we finished the theoretical part of our paper. So now from this slide, we are going to start with the implementation aspects. So now we provide a practical algorithm for implementation in the first scenario, which we call to be known types, where the teams are known upfront. So here we initialize the algorithms we initialize both the eval nets and the target nets for all the agents. So the popular DQN that was released by ME and others in 2015 gave this concept of using a separate target network for all agents. So we are just using all that from established principles. So we initialize the Q eval and Q target net. And then using the Q networks, we select an action based on the current state and the Q value estimate. And then we compute a new mean action for all the types. And this happens for every agent. Then we execute the action and observe the reward and the next state, which we do this for all the steps. Then we store the experience tuple, and we update all the Q networks as done in normal practice, as defined by ME and this in their seminal paper on deep Q learning. And this happens for all the episodes till we end the process. So in the next slide here, we are going to talk about the second scenario, which is the unknown types. The structure of the algorithm is same as what we discussed before, except that the types have to be determined during runtime, and it's not given to us upfront. So here, all the differences from the previous algorithm has been given in brown. So we maintain a buffer with the last actions, and then we update the Q networks as done in normal practice. After we get the experience tuple, we update the buffer with all the new actions, and then we perform a k-means clustering on the buffer. And using this clustering, we obtain the types, and we assign agents action to types, and we continue to update in normal practice. So this is all for the implementation details. I'll make a small pause for questions.
I think there were no questions on this part specifically. Thanks.
Okay, thank you. So now we go to the experiment section. So we design all our experiments in MAgents, which is an open source framework that supports learning of many different agents in the environment. So we perform these experiments on 3 different games designed in the MAgents testbed. In the first game, which is the multi-team battle, we have 4 teams with 72 agents each fighting against each other to win a battle. So thus there are a total of 218 agents at the start. So you can appreciate how big this is. Most multi-agent algorithms in literature deal with only tens of agents, but here we deal with hundreds of agents. So in the first figure here, each color represents a different team. The objective is to kill as many enemies as possible and simultaneously survive as long as possible. The second game here, which is the battle gathering game, is similar to the first one, but the agents can additionally capture food to gain more rewards. The third domain, the predator-prey, has two kinds of agents, the predators and the prey, with clearly different objectives. The first two domains are modeled as a known type domain, and the third domain is modeled as the unknown type domain. In future slides, in the further slides, I will discuss these domains in detail.
Okay, we did get a question for the previous slide. I think they were just trying to type it up. Is the buffer the place that you do the averaging, and do you replace similar actions using k-means with their centroids?
No, so we don't replace actions using centroids. So the buffer is only to determine types. So what we do is we store all the actions as they come into this buffer, and then we do a k-means clustering on the buffer. So when we do the clustering on the buffer, that will clearly cluster all the, let's say there are n agents in the environment. So that will clearly cluster all the n agents in the environment into m types. So once we get each type, we will assign the action of a particular agent to its individual type, and then do an average over the type. Hopefully that was clear.
Thank you.
Okay, so just moving on with the experiments. In the first, so for the first experiment, for the first domain, multi-team battle, we conduct experiments actually across all the three domains, and using a two-stage process. In the first stage, we train the networks by playing 4 teams that learn using the same algorithm. So during training, the algorithms don't know what kind of opponents they will face. So they will just clone themselves and fight teams playing the same algorithm. So in the second stage, we have a face-off where the trained teams fight against teams trained by other algorithms. And the reward function mirrors the notion of type, which I briefly mentioned before. So each team has a favorable opponent, which it can kill to get more rewards than other opponents. The winner has maximum agents alive at the end of the competition in the test phase. So moving on to the results, the 4 algorithms that we consider here are MFQ, which is a shorthand for mean field Q learning. This algorithm has been introduced by Yang. MFAC, shorthand for mean field actor critique, also introduced by Yang. IL, independent Q learning, which is a well-known multi-agent reinforcement learning algorithm. MTMFQ is the multi-type mean field Q learning algorithm, which is introduced by us. So in the first figure here, you can see that the MTMFQ algorithm obtains a lead early on and maintains the lead throughout. The other 2 algorithms, ML and MFQ, have to do a lot of work to catch up with this. MFAC falls into a bad local optimum early on, and it never really comes out of that. The next 2 bar plots are for the second stage, which is the test stage. You can see again MTMFQ in a face-off with the other 3 algorithms is clearly able to take a lead and able to maintain that lead for both the plots. The first one is for the total rewards, and the second one is for the win rate.
We did have a quick question. Sorry to cut you off here.
Yeah, sure.
So a question was, would the implementation of later improvements to DQN, for example, distributional reinforcement learning, have an effect in the mean field environment?
Yes. So most of the improvements for the DQN that people have seen or people are talking about is for the single agent scenario. So the critical difference between the single agent scenario and the multi-agent scenario is that in the single agent scenario, the transition dynamics or the transition matrix can be assumed to be stationary. And most of the improvements work very well for that setting. Now, when you come to the multi-agent scenario, because the agent dynamics are, because the environment is dynamic, like the transition dynamics is not stationary anymore. So it is not intuitive, or it's not clear, or how these algorithms will perform. So in most cases, we see that the algorithms don't perform well. The improvements actually, the improvements to DQN, in most cases, we see that the kind of successes they have in single agent settings don't extend to multi-agent setting. And this is a bigger version of multi-agent setting. It's a many agent setting. So I'm skeptical about how they will perform in these settings. I don't think the successes will naturally correspond in these settings.
Gotcha. Thank you.
Thank you. So let's move on to the second domain, which is the battle gathering domain. Like I mentioned before, this is similar to the multi-team battle, except that we have food in the environment. and which the agents can capture to get additional rewards. So the objective here is threefold, as against being twofold in the previous game. The agent has to capture food, or it also has to be able to kill and survive. So we have so this domain is arguably harder than the multi-team battle domain. So even in this setting, we see that MTMFQ obtains a lead early on and maintains a lead throughout. And this can be seen across both the stages, the training as well as the test stage. So in the third setting, which is the predator-prey domain, we have two distinct types of agents, which is the predator and the prey. The prey are faster than predators, and the objective is to escape from the predators. The predators are more powerful than the prey, so the objective is to kill prey. The MTMFQ here uses the k-means to model the opponents, because like I mentioned before, this is an unknown type domain. And we start all the games with more prey than predators, because this makes it more fair. At the end, the team that wins the competition is the team with more number of agents, the maximum number of agents alive. So now the predators have to kill a lot more prey to win, whereas the prey has to survive longer. With the results again, we see that MTMFQ has a clear lead over the other baselines across the two stages. Thus, we can see using all the three experiments that explicit type modeling helps, and this confirms our theoretical results as well. So that concludes our experimental section, and let me pause for questions.
Right. So there was, I guess I have a question as well for the Nash equilibrium part that you have mentioned, I guess, some slides before. Because I guess to get the Nash equilibrium, right, for, let's say, the predator and the prey, like, do you have kind of different, because I guess you would still need some sort of reward function in a sense, right? So each kind of agent knows what is the best action for it, right? So to get the Nash equilibrium, would you also have the same, I would say, like, reward function or like cumulative rewards, like for those?
Yeah, so that's a good question. So what happens here is each agent has its own reward function. So the Nash equilibrium is a solution concept by definition, which means that given the strategy, it only means that given the strategy of all the agents in the environment, the agent playing a particular strategy has no incentive to deviate. So each agent will have their own reward function or their own payoffs. They can have their own utilities. There is no assumption in the Nash equilibrium there is no assumption for the utilities itself. So each agent can have their own utilities, but because the agents are rational, they are only trying to maximize its own utility. So we have no problem in having the predators and prey to have their own different reward functions with respect to the Nash equilibrium as a solution concept.
I see. So they're kind of like greedy with respect to their utility functions themselves.
Yes, that is the assumption of rationality in game theory.
Gotcha. Thanks.
Okay. So here, let me clearly lay down the contributions of this paper. We have extended the notion of mean field theory to multiple types in multi-agent reinforcement learning problems. The many agent interactions has been reduced to a finite number of interactions using types, and we proved that this setting is still tractable. This is not a two-agent interaction as done by Yang and others, but it is a finite number of interaction. We have theoretically and empirically showed the advantage of types. One drawback of using types may be an increase in computational requirements, but still we showed that this approach is tractable. So now let me go back to the smart grid example briefly mentioned by Matt in the beginning. We can see that there are many different consumers of energy here, and the power grid has to manage power supply commensurate with demand for all these agents. The power requirements of something like factories would be much greater than houses, but they will have comparable requirements across different factories. Similarly, different houses will have a lower power requirement than factories, but they'll have comparable requirements across their own types, across different houses. Similarly, different offices will have different requirements as compared to industries and houses. Now we can see that the mean field assumption of independence and indistinguishability will work for agents of the same type, but is hard to justify across types. We focus on games for all the experiments, like many other research publications, but this is a very good real-world example that shows that our research will be useful. So as future work, we would like to consider more complex environments in financial and environmental domains. We would like to extend this work to completely heterogeneous domains like StarCraft. We would also like to consider subtypes, which can further divide types. Thank you for your attention. I have a couple of important links here for the paper and the code, which has also been given in the link for the talk. If you have any questions, feel free to email me at this email ID. But I think we still have some more time for questions, so I'm available to take more questions. Thank you.
Yep. Thank you so much for the talk. We do have some questions here, so I will go ahead and relay them. So the first one is, doesn't the non-stationarity of the environment introduce bias when sampling from the replay buffer?
Okay, so here we maintain a replay buffer for each. So each agent is assumed to be independent, and each agent has a replay buffer for its own setting. And therefore, so what we have here is the replay buffer has the experience tuple, which consists of the state, the average action, as well as the action performed by the agent. So that is the experience tuple here. So the experience tuple clearly integrates the actions of other agents too. So in a sense, that is not that will mitigate this effect of non-stationarity.
I see. Thank you.
But I would also point out that this is a problem in general for replay buffers that people are actually actively thinking about. It's because you don't want to just ignore your past experience, but as your past experience becomes less and less relevant because your own policy has changed or the environment has changed, maybe you shouldn't use it. So it's a very interesting research question that people are exploring.
Gotcha. Thanks for adding that. Sriram, did you want to mention something?
No, I'm good.
Okay, great. I will ask if they have any clarification on that,
Yes.
but I'll go into the next question. Could you please comment on the time-space complexity of, I assume they mean the experiments or the results that you were running?
Yes. So the Nash equilibrium paper from Hu and Wellman and showed that the Nash Q learning algorithm that they introduced was exponential in the number of agents. If I'm remembering right, is polynomial in the number of states, and so linear in the number of states and polynomial in the action space. So linear in state space, polynomial action space, and exponential in the number of agents. So our algorithm, canonically, because we base a lot of our work on them, would be exponential in the number of types, because we model types to represent groups of agents, will be exponential in the number of types, and the other guarantees are the same: linear in the state space and polynomial in the action space. If that answers the question.
Actually, a related question. Can you remind me what the wall clock time was and what kind of compute resources you needed to run one experiment? Because that might surprise people, the complexity required.
Yes. So actually, I ran all my experiments with a couple of GPUs, with 2 GPUs and 60 gigs of RAM. And it took for all the training, it takes something close to 12 hours.
Right. So
for each experiment.
12 hours on a simple video game. So because we want to move this to real world domains, thinking about more efficient compute is important as well.
Yes.
It's a very good question, Matt. Thanks for that. I was curious about that as well, so you read my mind. So another question we have here is, what are your initial thoughts about how this could be applied to finance?
Matt may be a good person to answer that. We do have a number of official thoughts, or initial thoughts, I should say. But I'm not sure how much of those are proprietary. And since I don't work at Borealis anymore, I don't feel comfortable sharing that, unfortunately. That's why I think the emphasis on the energy domain is a bit easier to talk about. And there are high quality simulators in that area if you're interested.
I see. Maybe then you could elaborate slightly on the energy domain, perhaps?
Sure. So in this energy domain, if you see, you have different agents with power requirements. So I'm modeling agents with I'm modeling objects with power requirements to be agents. So each agent will have a power requirement commensurate with its own demand. So we have, for a good example in this image is different types of consumers like electric vehicles, houses, and then factories and offices, which are connected to the same substation. So now this substation has to kind of manage the power supply, because there are some critical issues here. So if it's allocating a lot of energy to an agent which does not need it, then there are issues of like trips in your electric board, and then there are other potential catastrophes that can happen. And if it's going to allocate very less power supply, like energy, very less voltage to a particular agent, and let's say a factory, then the factory would not even run, because you're not able to run your machines anymore. So now the substation has to clearly define like how it wants to split up all its energies is in the perfect way possible, so that it's minimizing loss, and it's also minimizing any potential catastrophes because of oversupply. So for this to happen, you can very clearly see that if you just take a simple average, if you take a simple average of every agent over here, so everybody's demand, then what will happen is you have a baseline with which you're working, and you would just be giving the average demand to every single agent, to every single consumer, and that is not going to work because of the issues I just raised. So what then a good solution would be to divide all these people with power demands into potential groups, where within a group, all the agents within a group will have approximately similar demands, and across groups the demand would be vastly different. So this will make it easier for the substation to plan how to supply its energy.
Yeah, and to be a little more concrete, you could think of having different generators. So mostly I use solar, but if I need to fire up a coal-powered plant, I will. Should I turn that on? I could store water in a hydroelectric way, so you pump water to a higher gravity to store energy, and then you release that water to generate energy. So like a big battery. Should I be storing energy in that battery? Should I be releasing energy or keeping it the same? You could also think about, when should I tell consumer 53 that they should charge their car? So these are all really interesting decision theoretic questions, and being able to consider all of these different agents and their types rather than just thinking of the system, you should be able to get better results. That's our hypothesis.
I see. Just thinking about what you just mentioned, like I do have a question as well, because one of the assumptions was that I recall the action value pair is visited like infinitely often, right? So I guess for example, the energy real world example, how might you address, let's say, imperfect information with regards to, let's say, energy consumption or amounts that we're using to model, or if there are some action value pairs that don't really occur very often in the real world, how might you address that?
Yeah, so this is the actual problem, which is the trade-off between reinforcement learning in a virtual simulator and reinforcement learning in the real world. This is something that researchers are actively looking into, which is termed as real-world reinforcement learning. So how do you actually get all these experiences in the real world when you cannot have a simulator that is simulating this information for you? So there are a bunch of techniques that researchers have come up with in the recent past. So it's actually premature to say which will dominate in the future. It's still an active research area, and we are looking at a lot of active research in this domain in the next couple of years. But some methods, like lots of researchers in autonomous driving domain, they use reinforcement learning. Here again, you don't have a simulator, you can't simulate a lot of experiences, but they would actually try and use something like expert knowledge to leverage some existing model or to leverage some existing technique, so that you can kind of reduce the sample complexity in that way. There are also like techniques in which there are like techniques in the area of safety critic reinforcement learning, where there are certain experiences that is not possible because of safety issues. So there are a bunch of techniques there to handle such problems. I know Matt can provide more context to this.
And I think there's also two ways of thinking about Susan's question. So Sriram talked about one, that we could think about better ways of solving real world problems, which could include partial observability. So House 52 may tell you they have an EV that they want to charge and will let you control it. House 53 may have two friends come over with surprise new EVs they never told you about. So the partial observability is very interesting. But also, this paper makes a number of theoretical contributions, such as showing we converge if we visit state action pairs infinitely often. If we didn't have that convergence guarantee, it would be harder to get people to trust our algorithm and actually try it out. That said, in real life settings, you probably will not achieve optimal performance because you don't have infinite time, and other agents are coming into the environment, and pricing is changing, and the environment's non-stationary. So things are going to change before you could ever get to convergence anyway. So convergence is an important thing to have so that you know the algorithm is theoretically sound, but that doesn't always mean you're going to reach it in practice, which is why the speed of learning is often very important.
Yeah, that's a very, very good point there. That totally answers my question. In the interest of time, I'm going to wrap it up here. But Sriram, could you just flip to the very last slide so people know where to find you all? And yes, as the speakers have mentioned, some of the reference links are throughout the slide as well as here. So if any of you are interested, definitely reach out. And thank you all for joining. Thank you to the speaker.
Thank you.
Thanks for listening.
Thank you for the opportunity.